Okay, now for the sampling on XPU. This is a pretty straightforward process, honestly. With XPU, you basically add these pixel samples until things get clean. So let's start with 256. That's a pretty decent number of samples. And on the light sampling quality here, we'll turn that up to 2. Also, to save time, we can go to the Limits tab. We don't have any reflection. We don't have any refraction. So let's not waste time on that. And on the image outputs, we can get around the holdout issue by using Cryptomat. So go to Extra Render Vars, and towards the bottom, we have Cryptomat by object name. Okay, so as soon as we do that, we can then add in our terrain again, get all that nice indirect bounce lights. So let's go ahead and just grab the original geo, and again, do /***. That'll grab everything. Restart the render. And even though it looks kind of crazy because we have the terrain in there, because of Cryptomat, it's not going to matter because of the fact that we can just mask that out. Just to be sure, we don't need any camera effects, so turn that off. And I think that's everything we need. So I'm going to do a test render at 1920 by 1080, and let's see what the render time on that is. Okay, and at 256 samples, we end up with this. That took 4 minutes, 50 seconds. Which, by the way, if we compare the CPU of an hour down to 4 minutes here, that's the difference between you having a life and not having a life. So it's a massive, massive improvement. And because of that, let's just forget all about the CPU karma, because this is way worth it. Now, we still have some noise going on right here, so we're not done trying to crank up the samples, but I just wanted to point that out and show you guys how awesome that is for 4 minutes, 50 seconds. Let's multiply this times 1.5. That will give us 384. Let's see what happens when we do that. Okay, and at 7.5 minutes, we have a much better results. Before, after. It's still a bit grainy though, so let's actually multiply this whole thing times 2. And I'd also like to point out that we are getting a little bit too wispy up here. So I'm going to change the density ramp even more so that we don't have that weird wispy look up here. So let's go ahead and go back to the object level, go back to our density ramp, and looks like we need a bit more right there. So we'll do just that. And as soon as we have that, go back to the stage, and then take our render settings times 2. Let's see what that does. And at 9.5 minutes, we're looking pretty good. If we go to our crypto object though, that did not actually work. Maybe we can get lucky by switching that over to the material-based Cryptomat. So let's go down here and towards the bottom by material name. Let's do a quick render of all that. So turns out that 512 worked pretty good. Let's see if we can at least get the Cryptomat working. Well, looks like that does not work either, unfortunately. Well, let's see if we can get creative with this. It's, you know, there's only so many options you can run through before you start running out. But let me think about this and I'll get back to you on that. All right, guys, so there are 2 options that you have for rendering this out and getting a proper alpha to cut this out and comp it into any plate you'd like. With XPU, it does not support holdouts. And I should back up a second and let you know that if you want to see the alpha of an image, as an example, this color pass right here, you go down to this tiny little checkbox right here. and that lets you see the alpha of the image. This entire time, I've been spacing out and trying to go through these options to find the alpha, but in all reality, the C, which should be called beauty, the beauty pass alpha can be accessed by clicking on that small little button down there. So here nor there, the fact is you can't get this alpha to go black on the terrain with XPU. The feature is just not in there right now. You can't do it with the matte shader. You can't do it with a holdout. So if you want an alpha, you need to render this out using the CPU version. And so that kind of puts us in a situation because the CPU was taking forever. And even if you want to just use the CPU render for the alpha, that'll still add an extra 4 or 5 minutes to your whole render, even at low render settings. So in other words, you could try to just do a CPU render just for the alpha and then a GPU render that would be around 10 minutes or so. And that would take your total render time up to 15 minutes. Or I found a way to get the CPU render time down to around 15 minutes with a noise level that's not too bad. So unfortunately, there's just no clean way of working with this situation right now in Karma. In the future, this will probably be changed. They'll probably update the ability to, make a matte or a holdout for the things you don't want in the alpha, but right now it doesn't exist. So back here at our Karma render settings, there's a few things that are going to help speed this up for you if you're using Karma. One is the screen door samples and the volume step rates. Here in the user docs, we have a nice visualization for what this is trying to do. The screen door limits, in other words, stochastic sampling, allows you to sample a volume multiple times as it goes through the medium. And so that makes it easier for a sample to detect a positive voxel value. What that does visually is this. Let's go back to our scene, set the screen door sample to 1, and for right now, set the pixel samples to a low value here at 4. We'll go ahead and render this out, and I want to show you what happens when we don't have many of these samples going on. So without many screen door samples, it's very easy for Karma to miss out on low density values. Notice how towards the edge here, we are sometimes finding voxel values, we're sometimes not finding voxel values, and so it's having a hard time recognizing where the volume is. That's because as we go through the medium, as we're trying to sample through here, it may not actually have enough samples to detect a positive voxel value. And so, let's see what happens when we keep our pixel samples at 4, but we turn the screen door samples up to a big value of 128, just to really exaggerate this. And try that one more time. As we can see, we now have the ability to find those areas of low density, and the overall quality is greatly improved. So that's before at 1 screen door sample, and this is 128. So that's a massive difference, and our render time isn't that much more. This took 51 seconds, this took 12. And so for the level of quality that you're getting, it's a really good deal to add more screen door samples or more stochastic sampling to your volumes. So what does that mean? Well, it depends on the number of pixel samples that you're trying to go with. If we take this up to a value of 8 as an example, we double that. We might have enough to actually have a clean render when we have this all the way at 128. So let's try that one more time. So this is now looking a lot cleaner. It's still not quite there. If we look from back here, this might be clean enough to get away with it, depending on the situation. I do think it's probably best to be a little bit safe. This is about borderline what you can get away with as far as graininess from this distance. So let's turn it up a little bit. We'll go here to our pixel samples and do a value of about 12 on that. And then down here at the screen door samples, let's do 180. And after a couple of minutes, we end up with this, which is pretty good if we zoom out all the way back here. So we could probably push this a tad bit further, but let's use this as a baseline for right now. And then at the very end, if we still have noise, we can turn something up, but this is a good place for us to start on these render settings. So the first thing you do is you dial in those stochastic samples with your main pixel samples up there. And now let's talk about the volume step rates. So here's the idea with the volume step rates. When a pixel sample goes into your scene and it hits an area of voxels, is it going to consider the value of every single voxel as it travels through the medium? Or can it generalize what it finds by, let's say, only sampling 1 out of every 4 voxels that it encounters? That's what the volume step rate allows you to define. It's a way of speeding up your render by basically saying, okay, you don't need to think about every single voxel you encounter. Maybe you only need to think about 1 out of every 4, 1 out of every 2 voxels, whatever rate you set here. And so a value of 0.25 says only look at 1 out of every 4 voxels. A value of 0.5 would say only look at 1 out of every 2 voxels. And if we said 1, it would be saying look at every single voxel when you're trying to figure out the proper pixel color based off of that area that you just sampled. And so this is different than what we have up here in the stochastic sampling, because I believe that's all the way up here. Yeah, the stochastic sampling is how many times it's going to sample as it goes through the medium. This is saying how many times, or I guess how many voxels do you have to pay attention to. And so it's kind of difficult to understand the nuance of the difference here. But in general, think of the volume step rate in a way as down-resing the detail of the voxel values. And by down-resing it, in terms of its detail, you can make it go a lot faster. So here's what that looks like, okay? So what we're looking at right here is 0.25 at the volume step rate. That means it only paid attention to 1 out of every 4 voxel values it encountered. As we, let's say, bring this down to 0.1, right here, we're saying only listen to 1 out of every 10 voxel values that you encounter. And notice how the density got a lot less intense. It's not picking up as many density values anymore because, again, it's only considering 1 out of every 10 voxels when reading those values. And also look what happened to our detail. So keep your eye on the right area over here. Before, after. We lost a lot of detail in the process because we're generalizing the values when we bring that volume step rate down. When we say that you don't have to worry yourself about all the voxels anymore. If you bring this to an extreme, and I say only listen to 1 out of every 100 voxels you encounter, we end up with this. We have no detail. This might as well be a down-resed, VDB cloud. The VDB cloud, by the way, is not actually down-resed, but in effect, it's down-resed because of the fact that you're only listening to 1 out of every 100 voxels. All that data is there, it's just listening to a very small fraction of it. So that's a good way of thinking about it. And as you can see, we don't pick up that density. Everything is just getting very generalized. There's no detail. And now let's go back to Houdini and take a look at a volume step rate here of 1. So we liked having a screen door samples of 128. We like that with the 12 pixel samples. That's all fine. But there's one more catch. When we, let's say, decide to listen to every single voxel value, that's going to act as a multiplier says that right here, a multiplier on the total number of samples for volumetric objects. So what that means is that we have to change our screen door samples based on what we specify in the volume step rate. So now, before this was 0.25, right? We like that. These were the magical settings that gave us a baseline. Now I'm saying listen to every single voxel value. And by doing that, now it's going to essentially increase the number of screen door samples across the entire render. So I'm going to divide that by 4, because now we're again listening to every single voxel value. We don't need as many samples because that is getting multiplied by the number of times we read a voxel value. And so that now brings us down to 32. I can also go to the top here at our pixel samples and divide that by 4, giving us 3 pixel samples. Here's what that looks like. So this rendered in 1 minute 44 seconds, listening to every single voxel value it encountered. Compare that with this. As we can see, the density got more intense because it recognized all those values. And this is pretty darn close to what we had originally, except that there's more density and more details showing up. So I personally like listening to every single voxel. I want to get as much detail as possible out of this volumetric cloud. The density here is too much, so we're going to turn that down in our shader. But I just want to show you guys the difference between those two. All right, and after doing that, now here in the shader, we end up with this. Now do be careful though, because if your pixel samples here are too low, then you're going to lose quality when it tries to figure out motion blur. Now do be careful about these pixel samples though, because if you get too low, you're going to have a hard time figuring out motion blur. So I know this will increase the render time by quite a bit, but I'm going to say a value of 6 is good on this pixel samples for right now. Let's go back down here, see that we have 32 screen door samples, and see what that does. And after doubling our pixel samples, that brought our render time to about 5 minutes, which, as you can see, is about double to what we had before. But the quality is pretty awesome, honestly. This quality works really great from all the way back here. In the next video, let's talk about indirect rays. We don't actually have any bounced light, any of that going on right here, so we'll address that in the next video.